The Department of Computer Science and Engineering of CSEJISCE College of Engineering started its journey from the inception of the institution year of 2000 and is one of the prestigious departments for its ability of research and development activities apart from the regular academic work. CSE approved intake of 180 students in each year in B.Tech course and intake of 18 students in each year in M.Tech course and lateral intake 10% of total intake. The Department of Computer Science and Engineering of CSEJISCE College of Engineering is led by Professor Dharampal Singh. The department has traditional and smart classrooms to ensure that the students get complete and updated facilities. The faculty are dynamic and have a strong tradition of mentoring and guiding students towards achieving goals and fulfilling them, keeping the social responsibility as its central core. The department encourages students to explore new technologies by conducting workshops, national or international webinar, guest lectures, certified trainings, and other technological events like project, paper presentations, and also provides various opportunities to the students to engage in technical and non-technical activities beyond the classroom, like student clubs, sports activities, in-house coding competitions, cultural competitions, CSI activities, and more.
Hey everyone, my name is Shankhu Chatterjee. I am a student. I was a student of CSEJISCE College of Engineering. I graduated back in 2005 in Computer Science Department. I came back today to give a guest lecture on data analytics. Well, after coming to this college, I have seen a great change. It feels great back over here. The college that we saw when we were studying over here was totally different, and now the way it has evolved over years, right? It's been amazing. It feels great to be back and to give this lecture, to get that opportunity to give this lecture in front of the students. It's a great opportunity, and thanks a lot to everyone for giving me this opportunity.
Good evening, everyone. Myself, Polmi Mondol from Department of Computer Science and Engineering, CSEJISCE College of Engineering, Kalyani, Noida. A warm and a hearty welcome. I want to welcome everyone in this webinar series, Scope and Opportunities in Research and Higher Studies. And today is the day 5 of this webinar series. Our today's topic is cybersecurity and cryptography, and our today's speaker is Dr. Bikram Sarkar, respected professor of Department of Computer Science and Engineering, CSEJISCE College of Engineering. Before starting the session, I want to say a few words about our today's respected speaker. Dr. Bikramjit Sarkar is a productive computer science researcher and good R&D administrator with significant supervisory and analytical abilities in major areas of information technology, especially in computer security and e-governance. He has a teaching experience of more than 17 years in different organizations, government and self-financed in India. He is a chartered engineer and also the members and fellows of different professional societies like Center for Education Growth and Research India, Computer Science Teachers Association Chicago, Indian Engineering Teachers Association India, Indian Society for Technical Education, Indo-UK Confederation of Science, Technology and Research UK, Institute of Doctors, Engineers and Scientists India, International Association of Computer Science and Information Technology Singapore, International Association of Engineers Hong Kong, International Association of Professional and Fellow Engineers USA, and International Society for Research and Development UK, Institution of Engineers India, Nikhil Bharat Shiksha Parishad India. He has also been awarded with CMI Level 5 certificate by the Chartered Management Institute UK. Now, I want to request our total respected speaker, Dr. Vikramjit Sarkar, to start the session. Over to you, sir.
Thank you, Polomi, for this wonderful introduction. I am also thankful to the Department of Computer Science and Engineering, CSEJISCE College of Engineering, for giving me this opportunity to present before you all. So good evening, one and all. Today, I have arranged my presentation on the cyber security, targeting mainly the graduating students who have the interest towards the higher studies and research. So let me share the screen first. So I hope it has become full screen, right?
Yes, sir.
No, sir, it's not full screen. You have to present it.
It's not full screen?
No, sir, you have to present it.
Sir, go to slideshow mode.
Yes.
Go to slideshow, then from beginning, you have to select.
Now is it right? Hello?
No, sir, it is same, sir.
Sir, it will be better if you select the full screen. That is.
Yes, I have done
that. Yes, sir.
I have done that only.
No, sir, I think it is a particular window is sharing.
Sir, go to share. You have to select the entire full screen. I think now it's okay.
Is it all right now?
Yes, now you click on PPT and go to slideshow. Yes, sir, it is okay.
Okay, thank you. So let me first start with a famous quote of Benjamin Franklin. And it was, 3 people can keep a secret if 2 of them are dead. 3 people can keep a secret if 2 of them are dead. That is, he meant to say, human tendency is that when told that something is secret and asked to keep it secret, people become quite eager to share that secret to everyone else around. So keeping secret is not that easy. So as you believe, we all are now living in the information age where there is a need to keep information of every aspect of life. And this information as you treat the other assets, are required to be treated as the asset only. And these assets need to be secured, right? So these days, actually the networks have gone global and information has taken the digital form of bits and bytes. The critical information now gets stored, processed in digital form on digital devices and open communication channels. Since information plays such a vital role these days, the adversaries are targeting the computer systems and open communication channels to either steal the sensitive information or to disrupt the critical information system. So these days, the need for this information security become a real challenge. So as you can see on the screen, this triangle is called the CIA Triad, which is the backbone of every secure system. So CIA, C for confidentiality, I for integrity, and A for availability. So this is actually the backbone of all the secure system. So confidentiality means the information needs to be confidential from the unauthorized access. So that is the confidentiality the system should provide. Next is integrity, means the system should ensure that no alteration is being made on this data while being communicated, right? And what about the availability? The availability ensures that the systems or the system resources need to be available to the authorized entities every time, always, whatever may be the situation. So if you can ensure all these three, confidentiality, integrity, and availability, you can secure a system. Now, in order to make a system secured or make some information secured from the unauthorized access, you can have two mechanisms to implement. One is the cryptography, and the second one is the steganography. In this session, I will mainly concentrate on the cryptographic text. Now, what is steganography? Actually, in case of cryptography, as you know, the information which are required to be kept secret from the unauthorized entities should be transformed into some unintelligible form, right? So there is some sort of transformation involved in the process. The actual information is transformed into some other form, and this unintelligible form of the message is being transmitted, so that the people who are not at all authorized to read the messages should not be able to have an access over that. Means they can have the access, but they will not be understanding the message, actual message. But in case of steganography, the message, the original message, is not getting transformed, but are kept inside one envelope of some other medium or the same medium, and this envelope is actually carried out to the destination. And while implementing some steganographic algorithm, you should keep in your mind that the envelope that is being passed means, envelope means what? A message itself. Say, for example, you have a text message. You have a message for your partner at some other point on earth. So your text message is actually embedded into some other medium, may it be text or may it be image, audio, whatever you like. Now, say for example, you have chosen a popular image of, say, Rabindranath Tagore for the envelope. And inside this image, you are actually embedding the text message as you want to send. Now the thing is, if after injecting those messages into this envelope, if the message, if the envelope gets tampered, means if it is visible to, if it is identified by the human perception, then there will be some doubt that this is not the actual image, or this image has somewhat been tampered. So this can be one envelope. So the adversaries will try to get out the actual information out of that. So this thing you need to keep in your mind while implementing the Steganography. Say, for example, you are person A is going to send one text message to person B. I'm just giving you an analogy of this concept of Steganography. Say person A is trying to send some message M to person B. Now say person A employs one person, say person C, to carry this information to the intended destination, that is person B. So person B A does what at the sending end, the transmission end? Say, for example, the person A makes this person C bald-headed. The person C, the carrier, is shaven by his head, and the message is put on his scalp by tattooing. Say, for example, now the person C, the carrier, waits for his hair to grow, and when the hair grows, the person moves to the destination. Now, if meanwhile, if he gets attacked by some adversaries, then the adversary, will not be in a position to understand that there should be some message inside the hair tattooed on the head of this person, the scalp of this person. That means what? The message is getting hidden inside the envelope, but the message is kept intact. It is not transformed like cryptography. It is just kept hidden. So that is the difference between cryptography and steganography. So in this session, I will mainly discuss about this cryptographic techniques of different sort. Now, what is cryptography? As you know, in cryptography, as I said, the original message is transformed to some other form, to some unintelligible form, so that the unauthorized persons do not understand the actual message. Right? So, some sort of encoding is involved in this process. And while we talk about cryptography, this encoding is called the enciphering, and the code that we generate after implementing the cryptographic algorithm at the transmission end is called a ciphertext, whereas the original message is called the plaintext. Right? And in order to transform this plaintext into the corresponding ciphertext, some key is required. And in this context, I want to mention one thing, that the algorithms that are used to encode the original message to some other form are all known to everybody, are all global, are all public. It is the key that makes the entire process confidential or secret. So, what did we say? The algorithm is public, but key is private. say for example, we are implementing say RSL algorithm or DES algorithm or AES algorithm. So there, everybody knows the algorithm, the process involved there, everybody knows that. But the key that has been, the private key or the secret key that has been chosen is not known to everyone else except the intended persons. So here lies the security of the system, right? Now, as per the general convention we use, the sender is termed as the Alice, the receiver is termed as Bob, and the adversaries, that is the intruders, are termed as Oscar in our discussion. The factors or the parameters that make this cryptography secure is the confusion and the diffusion. These are the two properties of any secure algorithm. So what is this confusion and diffusion? The confusion is employed for making uniform ciphertext, right? The confusion ensures that the ciphertext does not provide any clue about the plain text, right? The ciphertext does not provide any clue about the plain text. So that is the main concept of this confusion. And this confusion in any algorithm is achieved by the substitution, right? Means, say for example, consider one algorithm, say A, where we are using some key for the encryption, and say the original message is A and the transform message is B. So on seeing B, you cannot guess about the original message, that is A. So that is the confusion. So confusion hides the relationship between the ciphertext and the key. And if one bit of the key is changed, then all the bits of the ciphertext are required to be changed, right? And on the other hand, what is diffusion? The diffusion is a process that is used to increase the redundancy of the plain text, and it is achieved by the transposition or permutation or the rearrangement or rather reshuffling of the symbols present in the text. And it is used in the block cipher, whereas the confusion is used in both stream and block ciphers. So what is stream cipher and what is block cipher? In case of stream cipher algorithms, each of the symbols or each of the characters present in the plain text are encrypted character-wise, means individually. If the plain text consists that a string, say ABCD, so these 4 individual characters will be encrypted individually, and will be having some set of plain text ciphertext characters after the encipherment, right? Understood? Okay. So in diffusion, what happens? The relation between the ciphertext and the plain text is required to be kept hidden. And if the plain text word or the symbol is changed, then many or all the symbols of the ciphertext will be changed, are required to be changed. So that is actually the diffusion, right? So say a plain text is ABCD, and by implementing some algorithm, the ciphertext becomes DACD. That means those 4 characters A, B, C, D are present here also, but in different positions. Means the positions of these characters in the plain text are reshuffled in the ciphertext or permuted. So this is actually the transposition or permutation. So we'll be talking about this transposition substitution afterwards in detail. So this is the main concept to provide security in cryptographic techniques. Now, these cryptographic techniques can be classified into 3 categories. Symmetric key cryptography, and that is the classical cryptography you call. It is the ancient process of enciphering, and in comparison with this classical cipher, asymmetric key cryptography or the public key cryptography is a newer concept, and also there is a concept called hashing in cryptography. So in symmetric key cryptography, both the senders and the receivers use the same key for encryption and decryption respectively. So the key which is used to encrypt the plain text will be used to decrypt the ciphertext as well. So this key needs to be agreed upon by these communicating parties beforehand, so that both can be in a position to use the same key for their own process. In asymmetric key cryptography, what happens? One key pair is generated, right? Say there are 4 nodes connected in a network, A, B, C, D. So at one given point of time, A can communicate to B, means A can send some message to B. So at that point, A is acting as the sender and B is acting as the receiver. And say at some other time, C is communicating with D, means C is the sender and D is the receiver. In some other point of time, D can send some message to C or to A or to B. So anyone can send any message to anybody connected to the network. Now what happens? So at some point of time, the same node which is being used as a sender can act as a receiver at some other point of time. So the ultimate thing is each of the nodes play a role of the receiver at a certain point of time. And by the virtue of this fact, each of the receivers, means each of the nodes, generate one key pair, one public key and one private key. So everyone does it. So one private key and one public key is generated by each of the receivers. And these private key and public key are mathematically interlinked or logically interlinked in such a way that the message which is getting encrypted by the public key of the receiver will be decrypted by the private key of the receiver itself. So after generating the key pair, each of the receivers broadcast the public key, right? And everyone else who wants to send some information to that particular receiver will grab hold the public key broadcast by the receiver, get their own messages encrypted with that public key, and the encrypted message will be sent to the receiver. And on the receiving end, the receiver will decrypt that encrypted message by using his own private key. So here what happens? Two different keys are used for encryption and decryption in case of asymmetric key cryptography or public key cryptography. And hashing is also an important process for providing integrity, right? So in case of hashing, what happens? The sender, before sending the message to the receiver, use some cryptographic hash function to generate a fixed length hash code, or we call it message digest, out of the variable length message. Means whatever may be the size of this plain text or the original message, the length of this message digest or the hash code will remain same for the same algorithm, right? So this process is non-reversible, means you can generate a hash code from the message, but the reverse process is not possible. So what is the advantage of this process? So after generating this hash code, if we are not, say, concerned about the confidentiality, then if we are only concentrating the integrity, then what happens? The hash code generated from the message along with the message itself is communicated to the receiver. And on the receiver end, the receiver does what? He generates another hash code from the received message using the same cryptographic hash function. Now, the receiver has received one hash code and generated one hash code. So, he is having two hash codes with him. So, he will now, means Bob will now compare these two hash codes to ensure whether some sort of alteration has been made to the original message during the communication. So if the message is altered, meanwhile, the same hash code will not be generated out of that. So there, the receiver will get to understand that there is some sort of alteration in between, right? So now, if you want to make this system secure, so you can use some cryptographic techniques as well in association with this hash techniques. So with these techniques, you can secure the information being communicated from the transmission end to the receiving end, right? So this is the concept of hashing. So now onwards, we'll be talking about the classical cryptographic techniques. So here is the formal definition of the classical cryptography. That is the private key cryptography or symmetric key cryptography. So this classical cryptography is defined to be a 5-tuple: P, C, K, E, and D. This P is what? This is the finite set of all possible plain texts. Means P is a finite set of some characters, and the plain texts are formed or constructed using those characters only, which are thus elements from this capital P. This capital C is another finite set of all possible cipher texts. Means this this P consists of the all possible plain texts, and after encryption, using some key, whatever characters will be generated are all included in the set of C. And capital K is the finite set of all possible keys that these communicating parties can use for their communication. So capital K is the set of keys. So all these are defined. Now for each small k belonging to capital K, there exists one encryption rule EK, which belongs to capital E, and one decryption rule DK that belongs to capital D. So what is this capital E and capital D then? So capital E is a finite set of all possible encryption rules, and capital D is the finite set of all possible decryption rules. And what is this small k? Is any particular key, an element from the set of all possible keys, such that EK of X, what is X? X is the plain text. So we are imposing the encryption rule on the plain text X and getting Y as the ciphertext. And similarly, we implement DK over Y to get back X. So here X and Y are the elements from capital P and capital C respectively. So this is actually the formal definition of classical cryptography. And from this definition, you can have an idea of the classical cryptography itself. So this is the block diagram, as you can see. Here X is the plain text that Alice wants to send to Bob. But before sending it, she encrypts X to generate Y. And this Y is being communicated through the insecure channel. And there are the intruders always present, attempting to steal or tamper those messages being passed through this insecure channel. In an ideal case, what is received at the receiving end is Y itself. That is the ciphertext that has been generated at the transmission end. And this ciphertext is getting decrypted by Bob, and he gets back X. And as you can see, this small k, which is being used as the key for this encryption and decryption, are shared between these communicating parties through some secure channel. So this is the concept of the classical cryptography. And these are the properties of the classical cryptography that need to be satisfied. One is the encryption rules and the decryption rules should be computable. Means there must be some defined equations or expressions for this encryption and decryption rules so that you can get it implemented. 2, given a ciphertext, it should be difficult for an opponent to identify the encryption key and hence the plain text. Right? That means confusion. And the key space must be large enough. Right? Otherwise, the intruder might be able to break the system by using all the possible keys by the brute force attack, by the trial and error. Say if there are 5 possible keys, so at most 5 attempts will be required to break the system. But if there are 5,000 possibilities, then at most 5,000 attempts will be required. So we are making the system somewhat secure in comparison with the previous concept. So these are the properties you need to maintain. Now this is, I'm giving an example of this classical cryptography. There are the several classifications that we'll discuss afterwards, but right now I'm giving an example of this classical crypto system. The scissor cipher is the most simple algorithm, the simplest one. And why is it called scissor cipher? Because the Roman Emperor Julius Caesar used to use this concept, of course manually, during his personal communication. Actually, this concept of scissor cipher is based on shifting the characters by a number of positions. So that is why this cipher is also called a shift cipher or a scissors shift. Now let us define it as we define the classical cryptography in general. So as you can see, here we have defined P equal to C equal to K equal to Z26, right? So Z26 means the first 26 integers, Z26. So what are those? 0 to 25. So P has been defined as 0 to 25, C has been defined as 0 to 25, and K is also defined as 0 to 25. Now, why 0 to 25? Why 26? Because we have 26 characters in English alphabet. And for the simplicity, we are using only one case, say the uppercase, and there are 26 characters present, and each of the characters are assigned with some numeric value from 0 to 25. So A is assigned with the value 0, B is assigned with the value 1, and Z is assigned with the value 25, like that. So that means what? P is this 0 to 25. Because the plain text we are going to construct is all constructed by sum of the characters from A to Z, right? And similarly, the ciphertext characters also belong to this English alphabet from A to Z. So that is why we have kept P equal to C equal to Z26. But why K equal to Z26? Why not Z26 means 0 to 25? That means K is a finite set consisting of these 26 values from 0 to 25, means the key values are kept from 0 to 25 only. So why not 26? Why not 33? Why not 50? Why not 100? So you keep thinking. I'll discuss afterwards. And here you see the encryption rule EK, which belongs to capital E, is what? Y is equal to EK of X. This is the encryption rule in general. Now this EK of X is getting defined here for this scissor cipher. How? X plus K mod 26. Right? You are shifting. Say for example, the plain text character is say A or say B. Right? So what is the corresponding numeric value? It's 1. A is 0, B is 1. Now if you say use the key 2, so it becomes what? You are shifting by 2. It was B, so it becomes C, D. So the ciphertext becomes D. Now what is the corresponding numeric value for that? It's 3, right? So 1 plus 2. 1 was the numeric value for the plain text, 2 was the key. So 1 plus 2, it becomes 3, right? Which is nothing but the ciphertext, the D. But what happens if the alphabet is exhausted while shifting. So it comes back to the initial position. So after Z, A comes back. So in order to implement that circular approach, we have used this modular function here. So x plus k mod 26 is the encryption rule. So y equal to x plus k mod 26, and x is the decryption rule for this cipher is x equal to y minus k mod 26. So now we have defined our cipher, right? Now what about this k equal to z26? Since we are implementing this modular approach here, that means A comes back after Z. So if you use the keys beyond this range from 0 to 25, what happens? Using the key value 0 is similar to using the key value 26. Right? If you use the value 0 and if you use the value 26, you will get the same result. If you use a key value 1 and if you use a key value 27, you will get the same result. So going beyond the range of from 0 to 25 will give you nothing. So that's why we have kept this k defined as Z26. Understood, everyone? Okay, fine. So now let us see. Say this is the plain text we have chosen. We will meet, right? And the key value that has been agreed upon by the communicating parties is 11, right? So 11 belongs to a set from 0 to 25. So we have chosen the value 11 to act as a key. So first we need to find out the numeric values associated with this string we will meet. So these are the corresponding numeric values: 22, 4, 22, 8, 11, 11, 12, 4, 4, and 19. So we have here implemented the encryption rule, as you can see, and we have received these numeric values: 7, 15, 7, 19, and all. And as you can see, all these numeric values are also from the range from 0 to 25. And what are the corresponding characters? So these are the corresponding characters. H is 7, P is 15, like that. So after this conversion, we get the string HPHT WW XPPE. So this is the cipher text to be communicated through the insecure channel. Our original message was we will meet, but we will be sending this particular text. And if during the communication the intruder gets to access this cipher text, he will not be able to understand what the original message was that he will meet. You see? So that is the confusion. Understood? And on the receiving end, these are the numeric values associated with the string of the cipher text. The decryption rule is applied here. Y minus k mod 26. So same key value 11 has been used here. And as you can see, after performing the calculation, we received the same set of digits as before. You see here. That is the plain text. And here you see we have received the same set. So we will get back this original message we will meet. If not tampered meanwhile, this is the concept of Caesar cipher. Now, this Caesar cipher can be vulnerable to two different approaches. So, cryptanalysis process. One is the brute force. What is cryptanalysis? Cryptanalysis is a process for finding out the key used for the encryption of any algorithm. And if the key is accessed by the unauthorized entity, so every time the cipher text passes to this insecure channel will be accessed by the intruder, and by applying the decryption using the key that has been identified by the intruder, so this will be easier for the intruder to get back the original message if the key is once received or accessed. So there are two different techniques available for, breaking this system of Caesar cipher. One is brute force attack, and the second one is statistical attack. So actually, I am giving you a brief introduction of this techniques, and here we have been using the simplest algorithms for the understanding. So you see here, in case of Caesar cipher, as I said, capital K is a finite set of numeric values from 0 to 25. So how many elements are there in the set? 26 elements. And out of those 26 elements, one is the value 0. So if you use the key value 0 for this Caesar cipher, nothing will happen. The same thing will be generated, means the cipher text will be same as the plain text. So there is no use of using this key value 0. So you got 25 number of possible keys, right? Now that means what? At most 25 attempts will be required to break it, not more than that. Is it not? Now we see what the intruders perform in order to implement this brute force attack. So as you can see, this is the cipher text that the intruder accessed over the insecure channel. UVACLYFZLJBYL. So this is the cipher text. Since this is the insecure channel, I am repeating, since this is the insecure channel, everything passing through the channel will be accessed by the intruders. And so Oscar has received this string as the cipher text. And what is the role of this intruder then after getting this cipher text? He will try with all the possible key values to decrypt. So as I said, there are 25 possible keys for this case. From 1 to 25, he will keep trying with all the values of key. So when he uses the key value 1, he gets back this one, TUZBKXEYKI, like this. So does it make any sense? Absolutely not, right? So it proceeds with the next value, that is 2. Again, you got some other string as STYA, like that. So again, it has no meaning. So like this, it goes on. And when it comes to the key value 7, it gets this particular string, say NOTVER, like that. So does it make any sense? Yes, it is. Not very secure. You see, it has some sort of meaning, right? So from this 7 attempts, the Oscar, the intruder, will be able to identify the key being used, and that is the value 7. Right? Now, if the value a key value is 7, then the following messages, means the following ciphertexts that are being passed through this channel will be accessed by this Oscar and will be using this key value 7 to decrypt the message. That means the system is no longer remain secure. So this is how the brute force attack is implemented. Now, next is the statistical analysis of the statistical attack or the dictionary attack. Here, some statistics is maintained and used for this cryptanalysis. How? Here is a table. So this is the statistics we have before breaking the algorithm. So from this table, you see these are the letters and these are their corresponding frequency of occurrence in general. And from this table, you can see that E is having the highest frequency of occurrence, T is having the next highest frequency of occurrence, and whereas this Q, X, Z, these are having the lowest frequency of occurrences in any general text. Right. So this is the statistics we have with us beforehand in order to break the system. How? You see. So as I said, the cipher texts being communicated through the channel is always accessible to the intruders. So say at some point of time, Oscar, that is the intruder, gets this particular string, as you can see on screen, a long text, right, consisting of a number of characters. So Oscar will do what with this? He will find out the frequencies of occurrences of each of the characters present in this text. He will find out the frequency of occurrence of X, the frequency of occurrence of L, I, and all. Right? So on analyzing the text like way, Oscar finds out that I, the character I, has occurred 14 times here. V has occurred 13 times here. Like that. So for each of the characters present here, the Oscar will find out the corresponding number of occurrences in this particular text. So from these, he identifies that I is the character having the highest frequency of occurrence. Right. And as per the statistics, what was the character having the highest frequency? It was E. So Oscar will now try to map this E with I. Perhaps E in the plain text has become I in the cipher text. He will try to anticipate like that. So if that is so, if E in the plain text has been transformed into I in the cipher text, then what is the key value for that? E from I, F, G, H, I. So the key value is 4. If E maps to I. If E maps to I, the key value is 4. You understood? Now, Oscar will use this key value 4 on this particular cipher text for decryption. And after decryption, he gets this particular string Does it make any sense? Perhaps. You see, there is some sort of meaning associated with this text. The house is now for sale for $4 million. It is worth more hurry before the seller receives more offers. That means the string that we transformed by using the key value 4 is having some meaning. That means this 4 must be the corresponding key that has been used for this transformation. So you understood how some statistics is getting used to break a particular system? So this is the statistical attack. Now, as we mentioned earlier also, that substitution, transposition and all, here is the classification of these symmetric crypto systems. These are of two types: substitution technique and transposition technique. So in substitution technique, the characters of the plain text will be replaced or will be substituted by some other set of characters. Whereas in transposition technique, the characters present in the plain text will also be present in the ciphertext, but in different order. Means the order in the plain text will be reshuffled in the ciphertext. So that is actually the diffusion, right? Now this substitution technique can further be classified into two different categories. One is the monoalphabetic cipher and the second one is the polyalphabetic cipher. In monoalphabetic cipher, the mapping of the plain text to ciphertext is 1-to-1, right? Means if, say, algorithm A is being used for this transformation and the key value K is chosen, then the same character of the plain text will be mapped to the same character in the ciphertext always. Means if you use algorithm A and key small k over a message, say M, it will always map to the same character, that is, say, C. So mapping is 1-to-1, as you saw in case of scissor cipher, right? So if plain text is A and key is 2, then the ciphertext will always be C. That is the substitution technique. And in monoalphabetic substitution technique. So in polyalphabetic substitution technique, this mapping is 1-to-many or many-to-1. Means if you use the same algorithm and the same key is being agreed upon by the communicating parties, the same character will not be mapped to the same character. So let us illustrate with an example. So let us consider one more cryptographic technique or a cipher, say auto key cipher. Here you see P1, P2, P3, these are all the characters chosen from capital P to construct the plain text. And the key that this pair of communicating parties agreed upon is small k. So this key, as you see, is what? Stream of subkeys. You agree upon one particular key, that is, say, K1. K1 is the key that Alice and Bob both agreed upon. Now you see the actual key for this transformation is nothing but the stream of some sub keys, where the first sub key is the key that has been agreed upon by the communicating parties. The second sub key is the first plain text character. The third sub key is the second plain text character. The fourth sub key is the third plain text character, and so on. Understood? So here, similar to the scissor cipher, we have kept this P equal to C equal to Z26, and this is the key for this algorithm, where encryption rule, you see, PI plus KI mod 26, unlike scissor cipher where it was P plus K, and this is CI minus QI mod 26. Now let us look at this example. Say P is the plain text, K is the key, and C is the ciphertext. So what was the plain text we chose? Is cross the line. So it is the plain text, cross the line. Now 2, 17, 14 are the corresponding numeric values taken from this Z26 as before. Now key that has been agreed upon by these parties is 11. So 11 is the first sub key for this encryption. What is the second sub key? That is the first plain text character. Third sub key, second plain text character. Fourth sub key, third plain text character, like this. You see, 2, 2, 17, 17, 18, 18, 7, 7, 11, 11, 13, 13, and all. So what was the encryption rule? PI plus KI mod 26 means 2 plus 11 mod 26, that is 13. 17 plus 2 mod 26, 19. So like this we receive these results, and what are the corresponding characters? So this is the set of characters, that is NTFG KLAL PTVR. So the plain text was cross the line, and this is the corresponding ciphertext, right? And the deciphering is just the opposite of this process, just the reverse. Here, one thing you should note, that this AutoKey cipher is vulnerable to brute force attack, because this key value that you choose here, this small k, lies between 0 to 25, means is small. So easily one can break this system by using trial and error, right? But here you see one more thing. In the plain text, you see there are two S's, one S here, one S here. But you see the corresponding ciphertexts are different. Here S maps to G, and here S maps to K. So one to many, you see. And again you see here is one L in the ciphertext, and here is another L in the ciphertext, but the corresponding plain text characters are different. So mapping is many to one. So here, since the mapping is not one to one, either one to many or many to one, it is not possible to implement this statistical analysis. Okay. And what about this transposition technique? So we can illustrate the concept of this transposition technique by mentioning the concept of this rail fence technique. Rail fence technique is one of the algorithms which comes under the transposition cipher, and it can be of two types. One is keyless approach, another one is keyed approach. So let us first explain this keyless approach. Here we have taken the plain text. See this, meet me tomorrow. Meet me tomorrow. So we have arranged this set of characters column wise in this matrix, where there are two rows in this matrix. So since there are two rows, we call it depth 2, right? If there were 3 or 4, so according to the number of rows, the depths will change. But at the time of reading it out, or in order to finding out the result, we would be reading row wise. At the time of preparing this matrix, we put the characters column wise, MEETMETOMORROW, but while reading, we'll be reading row wise, MEMTMROETEOORW. So this will be your cipher text. And you see, the same set of characters are present in both this plain text and cipher text, but in different positions, right? So this is the rail fence technique, keyless rail fence technique of depth 2. And here you could have arranged these plain text characters row wise as well, but at that time you should be reading out column wise. So again, in that case also, the same set of characters will remain present in both this plain text and cipher text. That is, the same set of characters in the plain text are getting reshuffled, permuted in the cipher text, right? So this is another example of this auto key cipher, that is the keyed approach. And here we have taken the depth 4 type. Here you see, this is the actual plain text. Attack is postponed until I show. Here you see, for the spelling of until, you have taken an extra character L in order to make it simple, the process simple. So you see, all the characters are arranged in this particular matrix, right? So here we have arranged the characters row wise, you see. Okay. But if there were no extra L here, what would happen? This position, this position will be occupied by W, the last character of the string. And what about this? This would be occupied by some null or some designated character, right? So now, since this is keyed approach, we have taken a key, which is a sequence of some numeric values, some distinct numeric values, and the values are from 1 to 7. Why 1 to 7? Because there are 7 columns, you see, in this matrix. And what is the sequence? 4, 3, 1, 2, 5, 6, 7. So this is the sequence. So at the time of constructing the matrix, we arrange the characters row wise. Now we will be reading out column wise, but following this sequence. First, 4th column will be taken out. So what is the first column, 4th column? This one. that is ASUS. You see, ASUS. Then there is the third column we choose. So what is that? TODI. You see, TODI. So like this, we have extracted the columns as per this particular sequence and constructed the corresponding ciphertext like this. So understood? So this is the actual concept of the transposition. So due to several reports of failure in past, a number of algorithms came into the picture, and ultimately an algorithm called Reindoll was accepted globally by a standard algorithm, and the name of this algorithm, name of the algorithm was Reindoll and was used as the advanced encryption standard around 2002, right? And elliptic curve cryptography, ECC, has already been invented, but its advantage and disadvantages are not yet fully understood. So this elliptic curve cryptography allows to perform encryption and decryption in a drastically lesser time, and thus allowing a higher amount of data to be passed with equal security. However, as other methods of encryption, this elliptic curve cryptography must also be tested and proven secure before it is accepted globally for governmental, commercial, or private use. Another concept came into this picture very recently in comparison with the others, that is the quantum cryptography. So quantum computation is the new phenomenon, comparatively new phenomenon, right? So while modern computers store data using a binary format called a bit, here we use qubits, the quantum bits. I'm not going into the detail of this concept, but I want to say one particular thing, that this is a very fast to compute all the high-end computations. And consider RSA 640. In RSA 640, a number with 193 digits. Can you imagine? A number with 193 digits, which can be factored by 80 numbers of 2.2 gigahertz computers over the span of 5 months. One quantum computer would factor the same in less than 17 seconds. So can you imagine the speed of this computation? So in view of these facts, modern cryptography will have to look for computationally harder problems or devise completely new techniques for achieving the goals presently served by the modern cryptographic techniques. But you cannot guarantee the security of any algorithm. No algorithm has been able to provide the ultimate security. There must be some sort of vulnerability as well. So with this, I conclude here. So, Polomi, over to you.
Yes. Thank you, sir. Thank you very much for this very beautiful and informative session. Our participants in YouTube Live are also saying that this is a very informative and nice session. We are learning very beautiful things today. Thank you, sir. So now I want to move to the question answer round session. Participants, have any questions? Please post in the YouTube Live chat. Please ask any questions from today's session. Sir, can we wait for 2 to 3 minutes if participants have any questions?
Okay, fine.
Okay, so I think there is no questions from participants. So next move to another part. So I will want to request the present faculties over here to say some words about today's session. Please, sir.
Actually, follow me. I have one question because cryptography is my favorite subject. So,
Yes, yes.
BGS, sir, there is one question from my side. Actually, what we have seen that in cipher text is there, and after conversion of cipher text in the encrypted text, the size always increase. So, my question is that there is any algorithm which provide the less size after encryption and optimality and the security is high. Any algorithm exists? This type of algorithm exists, sir?
See,
Before,
actually, whatever techniques we will be following, there are so many techniques available. Actually, cryptography can be classified into different categories. So each of the techniques has their own principles and processing. But the thing is, whatever plain text we are using, we need to transform before transmission. And if that is a stream cipher, the same same number of cipher text will be generated as was there in the plain text. And if that is a block cipher, in there also we will be having the same number of blocks of the same size.
okay. Okay, sir. Actually, second question is that suppose in the future computing we are going for the quantum computing.
Yes.
So in quantum computing, whatever the cryptography algorithms are available, so they can solve the within the
Within
fraction
a
of
fraction
second
of
they can
second.
solve.
I mean, I just cited an example. From the example, you would imagine that what is the speed of these quantum computers. So if for implementing this confusion and diffusion, if you want to implement some high-end computations, if you want to involve in the process, so that will also be carried out very efficiently in lesser time.
Yeah, sir. Thank you for your answer, sir. And one more time, actually, I want to say that, sir, we have given the wonderful session. And I hope that the many participants, those who have joined from the YouTube live and from and also many faculty, also enriched by your knowledge.
Thank you,
And
sir.
we know that this is our motto of the department. We can provide the knowledge whatever we have. So thank you for the wonderful and mesmerizing session, sir. Thank you, sir.
Thank you, sir. So, any other questions or words? Ira ma'am, Pranati ma'am, Shonali ma'am. Any words about today's session? Okay. Let's move forward. So,
Yes.
yes,
It's a
ma'am.
very nice session. Yes. I hope all the participants, including students, research scholar, and faculties, have got various knowledge about cryptography and little bit about steganography. So it was a wonderful session. Thank you, sir. Thank you, Vikram, sir.
Thank you.
Thank you so much, ma'am. Ira ma'am, Shonali ma'am. Any words? Okay, so let's forward. Now we are going to the last of this today's webinar. I want to request our honorable HOD sir of Department of Computer Science and Engineering, Professor Dr. Dharmpal Singh, to convey the vote of thanks. Over to you, sir. Hello, sir. Sir, okay, so I
Hello?
think, yes, sir. Yes, sir. Over to you, sir.
No, no. So, no, no. You want to say anything? Hello?
No, no, sir. Yes, over to you, sir. Oh, please convey the vote of thanks.
Okay, okay, okay. So, at the outset, I would like to say the good evening to all the participants and the good evening to the everyone. In fact, so I would like to thank the our principal sir for the idea. Whenever we can organize any program, sir motivate us. Also, I would like to thank the first our Dr. Bikomji Sarkar because sir has given the wonderful presentation and after the attending the whole day class. So it is a very good thing from our department side. The faculty are always eager to do the tasks whatever we assign them, and they come always forward for the any tasks and any good thing from the department side. I will also like to thank our faculty member because as you know that for the any webinar, teamwork will be required. So we have seen that even our student work also as a team member. Many I can see Pavitro, Polomi throughout the 5 day session they were present in the session and for creating the YouTube live, creating the link, and also communicating with the expert. And also Devasri Madam, she act as a anchor of the at the beginning of the program, and thanks to the in fact all the speaker because I'm thanked that I'm heading this type of department where faculty always support the view of my, and I thanks to the Bikomji sir, Dr. Bikomji Sarkar, Dr. Parnoti Rachit, Dr. Ira Nath, and Dr. Sudipto Sahana. In fact, all the faculty because they are the speakers, so they are the main highlight of the program. But side by side, our all faculty, Mr. Purbo Pal, Mr. Sumanto Chatterjee, Mr. Dr. Amit Majumdar, and Debussy Madam, and our Jila Madam also, and all the lab staff. Because when you know that as time of the circulation of the email, everyone done their part. That is reason we are going to organize this type of successful program. So it is only possible by the team effort, and I hope that in the future, as our motto of the department, whatever the knowledge we have, we can share. Because all the faculty, those who have given the presentation here, they have more than 15 years experience that. So that is when we decided that whatever the knowledge we have, why we why we cannot share this knowledge to our student, because all of us have done the PhD 3-5 years back. So that is reason these things comes in our mind, and we decided that we can go further this type of webinar. And if you see the webinar, it all mix of our some hands-on concept, some theoretical concept. Also, the research-oriented concept is also there. Sometime I have seen the Madam Dr. Ponatira's seat webinar presentation. She also give the idea what are the opportunity for the data science, data scientist also there. So it is also give the impact to the person who working in the industry. They can also get the idea. Yeah, these are type of opportunity available, and we can go for it, and we can cultivate our career in a good way. So these are the different things we have decided, and you successfully done it. And thanks to all the team member, because what during the after the class hour, this is a very hectic that we can go for any webinar. But thanks to our team member, they have fully supported us, and at the end we are able to organize this type of wonderful program. And I hope that this program at least create some seed within all the researcher and student and some industry person, and they can cultivate this seed and make the victory. So thank all, and I will also like to thank our Povitro and Polomi, because throughout the program they have supported us after attending the classes. So they are in the same boat as our teachers. So thanks to all my students that, and we have seen that this is a Polomi and the Povitro become the integral part of our any webinar. So thanks to the Povitro and the Polomi. So follow me over to you, and this is the and good evening to the everyone and good night to everyone. And I hope that in this pandemic situation you are fine, and in the future program we can also join it. So thank you to the everyone, and follow me over to you.
Thank you so much, sir, for such beautiful and precious words. So, now we come to the conclusion of our session.
Yeah, Polomi, I want to say something.
Yes, sure.
So some participants are writing that for yesterday's session, so some technical difficulties is there. That's why we're arranging this that yesterday's webinar in Google Meet, and obviously we will provide the recorded link through YouTube, so you can check from there. No issues are there, so you can definitely find out the link in YouTube. We will definitely upload it. So what to follow me?
Okay. So we have come to the conclusion of our session. So at the last, I also want to thank you, Vikramjit sir, for such beautiful session. Now, with the permission of HOD sir and our today's respected speaker and all our other respected faculties, I want to conclude to this. Thank you. Thank you all.
Yes, sir. Thank you.
Yes, live.